1.1 is functions and models. We have some vocabulary words to start out with. These are terms we'll be using for the entire semester, so it's worth it to write them out and commit them to memory. Data is real-world information collected in numerical form. A function is a rule or correspondence that assigns to each element of a set called the domain exactly one element of a second set called the range. In algebra, you may have been given the quick definition that it's a relation where every x has exactly one y. Okay. There are several ways to define a function. You can define it by a set of ordered pairs, a diagram, a table, a graph, an equation, or you can just verbally describe a function. We'll see several today, and we'll talk about what makes these things functions. A domain is the set of all the first elements of the functions or the inputs. These are the things we use. The x variable is normally what we put into the function. So it's talking about the set of all of the x's. The independent variable is the variable that's representing elements in the domain. So normally we use the variable x for the independent variable. If you're talking about some data set involving time, normally time is made as the independent variable because it's something that cannot be manipulated. It can't be sped up or slowed down. It's independent. Nice way to remember that. And the range is the set of all second elements of the function, or all of the outputs. These are all of the y's. Okay, so when we're talking about the y's, the things that come out of a function, those are our dependent variables. The value of y depends on what you put into the function as x. So you put in an x and out comes a y. The y is dependent on the x. A scatter plot is a graph of ordered pairs, usually real life data. And we'll get into making those on your graphing calculator through the course. First example we can talk about is body temperature. So suppose a child's normal temperature is 98.6 degrees Fahrenheit. And the only thermometer available is Celsius, and it indicates the child's temperature is 37 degrees Celsius. If the function that relates Fahrenheit and Celsius temperatures is F equals 9/5 C plus 32, does this reading indicate that the child's temperature is normal? One way we can do this is by taking the Celsius temperature and putting it into the formula that relates Fahrenheit and Celsius. See what that is as a Fahrenheit temperature and see how it compares to the child's normal temperature in Fahrenheit. So the Fahrenheit temperature is going to be 37 degrees times the 9/5 plus 32. And we can just grab our calculator. 9 divided by 5 times 37 plus 32, and that equals 98.6. So our Fahrenheit temperature of 98.6 is what we get from a Celsius temperature of 37 degrees, and that's exactly the same as their normal temperature. So yes, the temperature is normal. So yes, the temperature is normal. Okay. Next, we'll talk about domains and ranges. You can find domain by looking at a graph. You can also find range by looking at a graph. You can find domain and range by looking at the table. Here they have plotted some points for us, just a scatter plot of points, and you can identify what those are. This is the point -5, -7. There it is in the table. Here's the point -3, -2. There we go. And on. They've listed all the points in the table. Well, going back to our definitions, the domain is the set of all the x's. So we are going to list these in roster notation. In roster notation, we just list from leftmost x value to the rightmost x value. We put a comma between each of those elements and close the curly brace, which indicates we are finished describing that set. So the range is done in a similar way. I'm going to set up a roster, but we're going from the bottommost y value, from the negative y's, all the way up through the highest y value. It looks like the lowest y value is a -7. The next y value would be a -2. The next y value is a 5, and then a 6. And you could have gotten that by looking at the table as well. Just make sure that you're not copying those numbers down and writing them down. If a y element is there more than once, you don't want to name it more than once. You list it one time, but you also list those y values from the bottommost y value to the uppermost y value. Now when it comes to looking at a graph like B or C, you're not going to be using roster notation. The reason for this is that there are infinitely many points along this graph. This is a nice, you can see that's a dot, but there are infinitely many of those dots all around. They're just emphasizing that this is the end of that graph, this is the end of that graph. So here, our domain cannot be written in roster notation because we can't possibly list all of the x values individually. There are infinitely many of them. What we do is use interval notation, and we start by naming the first x value that appears. That's a -3, and then all of these dots all along here, all those points have x values until we get to this, and that's a +3. And we're going to use square brackets to show that -3 is included. It's a solid point. And +3 is included. It's a solid point. So these in interval notation are equivalent to a solid point. When we talk about range, again, we're going from the lowest y value up through the highest y value. The lowest y value is a -30, and there are y values, infinitely many y values, up through 40. And those are both solid points, so again, we're going to use parentheses, or square brackets. Now, if this point, say that this point was open like that, then we would put a parenthesis there instead of a square bracket. As it is, it doesn't show a big open bubble, so we know that those are included points, closed points. Parentheses are used if you have an open point like that. It shows that it gets infinitely close to that value but does not actually include that endpoint. Same with this. We're going to read from left to right to find the values of our x. And we're going to go from -infinity to +4 and close it with a square bracket. Range is going to go from, well, the lowest y value that we have is 0, and that's included because solid, you don't see a big open circle. And it goes up and up and up forever. This goes up and up and up forever. So positive infinity. On infinity and negative infinity, we always have a parenthesis. Just think about the fact that you cannot contain infinity. So the square bracket means that it contains that number. It includes that number. So recognizing functions. We have several different representations of different relationships here, and we want to decide whether or not it's a function and explain the reasoning for it. Give the domain and the range for each of these. So here we have the PC industry celebrated its 35th year anniversary in 2010. The sale of personal computers in the US in millions of dollars by year X are shown in the table. They want to know, is S a function of X? Okay, so is this number of computers a function of the year? In other words, for every X, there must be exactly one Y. Do you have a certain year here that has two different values for Y? No, you do not. So this is a function. We're going to say why. It is a function because every year has exactly one sale number figure. It wouldn't make sense to have two 1985s in here and have two different numbers for those, because and then you would say in 1985 the sales was this much in millions and also this much in millions. It doesn't make sense for this type of a data set for that to happen. So yeah, this is a function. And what is the domain? The domain is going to be, in roster notation, 1975, 1980, 1985, 1990, and you can see that there is a pattern of every 5 years after that, so it's fine to go ahead and go to 2015 and stop right there. Now your range, there is no set pattern to the range, so you do have to list each of those numbers. So range is going to be 0.04, 0.76, 6.6, 9.5, 21.4, 46.0, 62.0, 83.8, 122, and that's it. And that's your range. All right, the daily profit, P, in dollars, from the sale of X pounds of candy as shown in the scatter plot. Is this a function of X? So is the profit a function of X? You get a certain profit, one profit for every value of X that you have. And the answer is yes, we definitely have. If you sell this much candy, then this is your profit. Sell this much candy, that's your profit. You're not going to say, well, if I sell 150 pieces or pounds of candy, that I get two different profits. That wouldn't even make sense in this type of situation. So yes, it's a function. Because the sale of X pounds of candy will yield only one profit. Not going to get two different profits by selling the same amount of candy. All right. We want to know what the domain and the range is. So again, we're going to use the roster notation. Range is 0, 50, 100. We can see a pattern that it's every 50, so that's fine for you to put the ellipsis dots there and finish the pattern showing that the last element is 300. And your range is negative 200, negative 100, 1050, 1800, and 2050. Remember, you're going from the bottommost number up to the topmost number for your y's for your range. All right, the number of tons of coal sold determined by the profit P that's made from the sale of a product is shown in the table below. Okay, so is this going to be a function? We definitely have only the x values are only stated one time, and each of those has exactly one y. So because every number of tons has exactly the same amount, or has exactly one amount for profit, then we know that it's a function. Yes, it is a function. Because each ton measurement of coal sold yields exactly one amount of profit. All right. And if we wanted to state the domain, then we would start by our x's. Let's go ahead and 0, 500, and they're going by 500s, so write a few of those, and then your last element of 3000, and your range is going to be a negative 100,000. Careful on the commas here. You might not want to include the separation commas there when you're doing your roster notation for the range. We've got 109,000, 480,000, and 505,000. There we go. And part D, A is the amount in a person's checking account on a given day. I find this a little tricky. If I were to give you a problem like this on a quiz or a test, I'd try and make it a little bit more specific, or I would accept your answer based on your explanation. So you can have on any given day X, you get this amount in your checking account here of A. It is possible to have two different amounts in your checking account on a given day. Maybe you start the day with $300 in your account, and then at the end of the day you have $280 in your account because you took out $20 from an ATM somewhere. So based on that, I would say no, this is not a function. If this was a little bit more specific on the wording and said A is the amount in a person's checking account at the end of a given day, then definitely at the end of the day there can only be one balance on that checking account. So in that instance, I would say that it is a function. So sometimes these can be a little bit tricky. Just explain your reasoning so that I can take your answer if you have a different answer. All right, we need to know if this equation is defined as a function of x. In other words, does every x give you exactly one y? Or can you put two different y values in here and get the same value out for x? Okay, well, one thing that you could do, let's say that I put in a y equals -2 or y equals +2 and see what happens here. -2 squared equals 3x minus 3. That's 4 is 3x minus 3. This is going to be 7 is 3x, so x is 7/3. If I put in a +2 and square it, then I'm going to have 4. You see what's going on here. And so you see that you have a single value of x being 7/3 comes from using a y value of either 2 or -2. So it's not the case that every x has exactly one y. Now, doing it this way, you kind of have to know ahead of time if it is or isn't a function. Another way you can do this is just with a little bit of algebra. If you want to try and define this y as a function of x, solve it for y. Right now we need to take the square root of both sides. So when you take the square root, you have to put a plus minus there in order to capture all of the solutions when you're taking an even root. So this means that y is going to be plus or minus this quantity. So you put in an x, and then the y is going to be plus or minus the quantity after simplified. In other words, a single x will give you two y's. So this is not a function, right? Not a function. On this equation, they want to know if the y is defined as a function of x. So it's a little different story than what we had before. It's already solved for y. Y is the opposite of x squared plus 4 times x. It doesn't matter what kind of an x you put in there, you're going to get a single y value for every x that you put in. This is a function. Y is a single thing of -x squared plus 4x, whereas this one was y is plus or minus. You got two y's for every x that you put in. And the vertical line test is a nice visual way to see if a relation is a function. If it's already graphed for you, you can use this and see if you determine if it's a function or not. So we have part A here. We need to know if this is a function or not. Well, the vertical line test says that we have a set of points in the coordinate plane, and here we have them graphed, and we're going to take a vertical line and draw it through, so you can picture just rolling your pencil through here. And if it ever intersects a graph in more than one point at a time, then it's not a function. Okay? So you can see here, this is not a function. It doesn't pass the vertical line test. And if you want to further investigate why that is the case, you can look here. Let's see if we put this point here is a 2 and some negative number, right? And this point here is a 2 and some kind of a positive number. So we put in a single x and we get two different y's. That vertical line is showing those points have the same x but different y's. So this is not a function. Now if we would do that same thing over here, then it would pass the vertical line test. So this is a function. When you roll your pencil across that graph, it only will ever hit one time. Okay, so we know for sure that yes, this is a function. Now function notation can kind of throw you off a little bit when you're first learning it. You just have to remember that when we're talking about functions and you see f with parentheses, it does not mean multiplication, it's notation. F of x is function notation for saying y. So instead of having x, y points, we have x, f of x points. And it actually makes it a nice tidy way to keep track of your x and y values that go together and without even having to do a t-table. So if I had something like f of x equals x squared, then if I wanted to evaluate this at a value of 3, then I would say f of 3. So in place of the x is a 3, so you know that in the function you're replacing the x with a 3, and you simplify. This is the input that was put into the function, and then this is the output. So f of 3 is 9. This also corresponds to the point 3, 9, if you want to think of it that way. Here we're given a graph and also given the equation for that graph. And we're going to use the points that are shown there to find f of negative 2 and f of 4. And then we're also going to use the equation to evaluate. So f of negative 2, we write that down. And some people like to, when you're first using functions, like to write this out as a ghost function where you just put parentheses everywhere there is an x. So we're writing something out like this. And so f of negative 2 is 2 times negative 2 cubed plus 5 times negative 2 squared minus 28 times negative 2 minus 15. And yes, you can definitely use your calculator on this. So it's 2 times parentheses negative 2 exponent of 3, and then arrow right to get out of the exponent there, plus 5 times negative 2 squared minus 28 times a negative 2 minus 15, and so we get 45. All right, so f of negative 2 is 45. So you can see on the graph using the points that that's the point negative 2, 45, and you can use the equation to find out that f of negative 2 is 45. Now we can do the same for f of 4. So f of 4 is going to be 2 times 4 cubed plus 5 times 4 squared minus 28 times 4 minus 15. So you can grab your calculator, and instead of typing that all back in again, here's a nice tool. Arrow up so that that expression is highlighted that you used before, and hit enter, and then you can go back and edit. So here we go. Got a 4. I'm going to delete the negative and change the 2 to a 4. It just overwrites it. And delete the negative, change the 2 to a 4, and then you're ready to hit enter, and you get, what do you know, 81. So f of 4 is 81. Remember, we said these points can be seen here, the input and the output. So -2, 45, 4, 81. So you see it both just by looking at the graph and using the equation to find those values. Right, the points on this graph in the figure give the number of elderly men in the workforce in millions as a function g of the year for selected years t from 1950 and projected to 2050. So they want us to find and interpret g of 2020. Well, g of 2020, they're giving you the hint that, hey, this is our x value right here. So we're going to find 2020 on the x-axis and go up, and it looks like the y value is 21 they're showing you right here. So 21. It's not enough to find it, we have to interpret it. When we say interpret it, it means in the terms of this problem. So don't just give me numbers. You want to use the language that's already there in the problem. The language says that in the year 2020, there would be 21 million elderly men in the workforce. And that's that. Okay, part B. What if the input, what is the input t if the output is g of t equals 19.6 million men? So I'm looking along here and I'm going to try and find the 19.6. There it is. We read down and the input is going to be the year 2030. Okay. And what can be said about the number of elderly men in the workforce during 2020 to 2040? So from 2020 to 2040, we're going from here to here. It is decreasing. So we can say that is decreasing. What is the maximum number of elderly men in the workforce during the period shown on the graph? Well, we want to find the highest y value, since the y value pertains to the number of elderly men in the workforce in millions. And so that's that 45.8. So we have 45.8 million, make sure you say million, men. Okay, and they didn't ask what year that was. They just said, what is the maximum number of elderly men in the workforce? So that's all they want, is the number of millions of men. All right, modeling. Another vocabulary word, it's a process of translating real-world information into a mathematical form. So it can be applied and then interpreted in the real-world setting. It's called modeling, and we most often use it in this text. A mathematical model is a functional relationship. It's usually in the form of an equation, and if it's not, we will be finding those equations. And it includes not only the function rule, but also includes descriptions of all involved variables and their units of measure. The reason for this is that you are the one getting paid to know the math. Whatever degree you're going for that requires this math course, they want you to understand the math and be able to explain that to your clients, your participants. So if they do not understand the math, they're going to depend on you to explain it to them in terms that they understand. They don't understand intercepts. They don't understand an increasing slope, but you can put it into words for them in the context of the problem that they would understand, that would answer their questions. Aligning data. Now, when we find a model to fit a set of data, a lot of times it's easier to use aligned inputs rather than the actual data values. Those data values of inputs can be rather large, especially if you're talking about years. Here we are, say if you're in the year 2015, that's quite a ways over on the x-axis for that to be an x value. So aligned inputs, you get it to where it's aligned to a certain value, but you do have to say what you've aligned it to. For instance, instead of using the year 1990, you can say X is representing the number of years after 1990, or T is the number of years after 1990. And that way, if you get a T value of 30, then you know that that represents the year 2020 because it's 30 years after 1990. All right. And that will make a difference on your models that you come up with, so be careful with that. All right, public health care expenditures for the period 1990 to 2012 can be modeled, that is accurately approximated by this function E of t equals 738.1 times 1.065 to the t, where E of t is in billions of dollars and t is the number of years after 1990. So what are the independent and dependent variables? So I want you to write this out in the words and then identify the variable that goes with it. What is your independent variable? Your independent variable is t. What does it represent? Okay. E of t is in billions of dollars, and t is the number of years after 1990. Number of years after 1990. And E of t is your dependent variable. E depends on the t that you put inside of it, and it represents the billions of dollars. So it's not just dollars, it's billions of dollars. So if you get an E of t of 2, that's not 2, it's actually $2 billion. Billions of dollars. So in this form, you can see what your input and output is and what it is as a descriptive way of stating it. What value of t represents 2010? So 2010 is how many years after 1990? That would be 20. So t equals 20 represents the year 2010. We want to approximate the public health care expenditure for the year 2010. So we are going to use this function that they've given us and put in a 20 for the t. Grab your calculator. You're going to do 738.1 times 1.065 to an exponent of 20, since we're letting t equal 20. So we end up with 2,600. Okay, so that's about 2,600. And what is that? It's not actually 2,600. First off, it's dollars, but it's in billions of dollars. Okay, so we have this as billions. So here's billions, here's millions, thousands, and hundreds. There we go. Oh my goodness, that's quite a lot. Okay, so 2,600,000,000,000 dollars. Oh my goodness, that's a lot. All right, use the model to estimate the public healthcare expenditure for 2015. And then they want to know, can we be sure about this estimate? Well, let's look and see what it gives us. Again, figure out what the t value is. What is the number that we want to use for t? For year 2015, t is going to be 25. You don't have to type this all back in again. You can just scroll up, hit enter, and then edit, making that 20 a 25 instead. And that is quite a bit more. We've got 3,563. About 3,563, and that's with a lot of zeros behind it, and that's 3,563,000,000,000 approximately. And can you be sure about that estimate? It depends on a lot of factors, but I would say step back and look at all the data that you were given to come up with this model and see if that's kind of within the pattern. But it doesn't sound like it's too much off. It's definitely skyrocketing. So I'd say, yeah, we could be moderately sure about that estimate. All right, that does it for this section. Good luck on homework. Let me know if you have questions.